I'm going to talk about the role of the observer in quantum mechanics. And as I hope to show you, this has implications for the viability of a philosophy called physicalism, which is a major theme of this conference. Materialism, in its modern form, or physicalism, is the idea that all of reality, including human minds and thoughts, consists of physical processes that can, in principle, be completely described and accounted for in terms of mathematical physics. Interestingly, and perhaps paradoxically, physics itself provides a basis for doubting physicalism. There is an argument based on quantum mechanics that minds are not completely reducible to physics. This argument has a long and distinguished pedigree. It goes back at least to John von Neumann in his classic book, The Mathematical Foundations of Quantum Mechanics, published in 1932, and to the physicists Fritz London and Edmund Barr in the late 1930s. In the latter part of the 20th century, this argument was defended by such eminent physicists as the Nobel laureate Eugene Wigner and Sir Rudolf Peierls. Physicists who have written books recently defending it include Henry Stapp of UC Berkeley and Ewan Squires of the University of Durham. Sir Rudolf Peierls, for example, said, "The premise that you can describe in terms of physics the whole function of a human being, including its knowledge and its consciousness, is untenable. There is still something missing." Eugene Wigner baldly stated that materialism, or a materialist view of the human mind, is not consistent with present quantum mechanics. One is naturally tempted to ask, especially if one is not a physicalist, how quantum mechanics could have anything to say about minds at all. Isn't quantum mechanics about things that can be physically measured and observed, such as particles and forces? Of course it is. But while minds cannot be physically measured, it is minds that in the final analysis do all physical measurements. And that, as we'll see, is something that cannot be ignored if one is trying to make sense of quantum mechanics. If one claims that it is possible in principle to give a complete physical description of everything that goes on during a measurement, including the mind of the one who is making the measurement, one is led into difficulties. This is an aspect of what is called the measurement problem in quantum mechanics. Though there's a lot more to say about this than can be said in a brief talk, I can give the gist of the anti-physicalist argument and discuss some common objections to it. The starting point is the crucial fact that quantum mechanics is inherently probabilistic. Of course, even in classical physics, that is the physics that preceded quantum mechanics and is still perfectly adequate for many purposes, one often uses probabilities. But that is just due to practical limitations. In classical physics, one could, in principle, dispense with probabilities altogether if one had complete information about a physical system. That is not true in quantum mechanics. One cannot eliminate probabilities from quantum mechanics. In fact, quantum mechanics is fundamentally about probabilities. Because this is such a crucial point, it's worth spending a few minutes seeing why it's so. The reason is connected to a fundamental feature of quantum mechanics called wave-particle duality. For centuries, people debated whether light was made up of particles or of waves. The answer turned out to be quite strange. The work of Planck in 1900 and of Einstein in 1905 showed that light, in a way that is quite alien to our ordinary experience and intuition, is both wave-like and particle-like. Later, Louis de Broglie and others show that this wave-particle duality applies across the board to electrons, for example, and to all other kinds of matter. At first glance, wave-particle duality seems not only mysterious, but blatantly self-contradictory. A wave is something that is spread out in space, while a particle is a point. A wave is something whose magnitude can be varied continuously, whereas particles are discrete and countable. To see the apparent contradiction, consider a simple thought experiment. Imagine a flash of light from which light waves ripple out in an ever-widening sphere in space. Let us suppose the light is nearly monochromatic. As the wave spreads out and travels out, it becomes more attenuated since its energy is being spread over a larger and larger area. Now suppose we set up a detector at some distance from the flash of light, just a box with an aperture and a shutter, in essence a camera. The farther away the detector is placed from the light flash, the smaller the fraction of the light it will capture. Suppose you adjust the distance of the detector or camera from the light flash and its aperture size and its shutter speed in such a way that it captures exactly 1/1000th of the light in the flash. You can do this because these features of the detector, its distance, its aperture size, its shutter speed, are continuous variables. The apparent inconsistency arises if one now decides to think of the light in terms of particles. Suppose the original flash of light contained, say, 50 particles of light, that is, photons. The picture is supposed to show that, but don't take the picture too seriously, because it shows particles of light in definite positions and going in definite directions, which is a classical, not a quantum idea. If there are 50 particles of light, each carrying approximately the same energy because the light is approximately monochromatic, and if the detector has been adjusted to capture exactly 1/1000th of the light, then it would appear that the detector must capture 1/1000th of 50 particles, or 0.05 particles. But that is impossible, since you can only have a whole number of particles. A wave, being continuous, can be indefinitely attenuated and made as small as you wish, whereas particles, being discrete and countable chunks, cannot be. Now, quantum theory resolves this apparent problem by saying that the detector does not capture 0.05 particles, which is impossible, but that it has a 0.05 probability of capturing one particle, or, to be more precise, the expectation value or average number of particles that it will detect if the experiment is repeated many times is 0.05. So wave-particle duality, which gave rise to quantum mechanics in the first place, forces us to accept the conclusion that quantum mechanics is about probabilities, a conclusion first clearly drawn by the physicist Max Born in 1926. Roughly speaking, in classical physics, one calculated what actually happens while in quantum mechanics, one calculates the relative probabilities of various things happening. A familiar example is the idea of half-life of a radioactive nucleus. Suppose a certain type of nucleus has a half-life of 1 hour. That means that a nucleus of that type has a 50% chance of decaying, of disintegrating, within 1 hour, a 75% chance of decaying within 2 hours, and so forth. The quantum mechanical equations do not and cannot tell you when a particular nucleus is going to decay, only the probability of it doing so within a given period of time. In quantum mechanics, these probabilities are encoded in wave functions. Wave functions and the probabilities that they encode evolve in time according to an equation that is called Schrödinger's equation. Now we've arrived at the crux of the matter. We're talking about the probabilities of events, events such as a nucleus decaying or a particle of light entering a detector. But there's something paradoxical about the very notion of the probability of an event. It does not make sense to talk about the probability of an event happening unless at some point it stops being a matter of probability and becomes a matter of definite fact. For example, suppose I say that Jane has a 70% chance of passing the French exam. That only means something if at some point Jane takes the French exam and gets a definite grade, either passing or failing. At that point, the probability of her passing no longer remains 70%, but suddenly jumps to 100% if she passes or 0% if she fails. If Jane never, ever takes the exam and gets a definite grade, then the probability 70% would have meant nothing in the first place. It would lose any meaning. In other words, probabilities of events that lie between 0 and 100% must at some point jump to 0 or 100%, or else they meant nothing in the first place. This raises a thorny issue for quantum mechanics. The master equation that governs how wave functions evolve in time, the Schrodinger equation, does not yield probabilities that suddenly jump to 0% or 100%, but rather probabilities that vary smoothly with time and that generally remain between 0 and 100%. Radioactive nuclei are a very good example of this. The Schrodinger equation says that the survival probability of a nucleus, that is, the probability of its not having decayed, starts off at 100% and then falls continuously and monotonically, reaching 50% after one half-life, 25% after two half-lives, and so on, but never reaching 0. In other words, because an exponential function never goes to 0. In other words, the Schrodinger equation only gives probabilities of decaying, never an actual decay. If there were an actual decay, the survival probability should jump to 0 at that point. To recapitulate the key points. A, the equations in quantum mechanics yield probabilities. B, to mean anything, those probabilities must be probabilities of definite events that happen or do not happen. C, when definite events happen, some probabilities should jump to 0 or 100%. However, D, the equations of quantum mechanics do not describe such jumps. So one begins to see how one might reach the conclusion that not everything that happens is describable by the equations of quantum mechanics, that is, by the equations of physics. So how do minds enter the picture? The traditional understanding is that the definite events that happen or do not happen in quantum mechanics are the outcomes of measurements or observations. The two words are used interchangeably. If someone, traditionally called the observer, checks to see whether, say, a nucleus has or has not decayed, perhaps using a Geiger counter, he or she must get a definite answer. When the observer comes to know that answer, his or her knowledge suddenly changes. And at that point, the observer has to set the survival probability of the nucleus either to 0% or 100%, depending on what he or she has learned from the measurement. This sudden change in probabilities must, of course, be reflected in the wave function that encodes those probabilities. The wave function must suddenly change. This traditionally is called the collapse of the wave function. Schematically, the wave function of the nucleus looks as in the top equation on this slide, as long as no measurement is made. The coefficients alpha of t and beta of t are called probability amplitudes. When no measurement is made, these amplitudes evolve in time according to an equation called the Schrodinger equation. If one makes a measurement at time capital T to see if the nucleus has decayed or is still there, the probability that one will find that it has decayed is given by the absolute value squared of alpha of capital T. And the probability that one will find that it has not decayed is the absolute square of beta of capital T. This is called the probability rule, or the Born rule, after Max Born, who proposed it in 1926. It is the way of relating the wave functions to the predictions of probabilities. Well, what does the wave function look like right after the measurement? Well, it depends on what the outcome of the measurement was. If the measurement showed that the nucleus had decayed, then the wave function looks like the first of the two equations at the bottom of the slide. But if the measurement showed that the nucleus is still there, the wave function looks like the second of those two equations. In other words, one throws away or cuts off the part or parts of the wave function that describe outcomes that did not actually happen, and retains only the part corresponding to what actually did happen, resetting its coefficient or amplitude to be a number of magnitude 1, because now its probability is known to be 100%. So you can see that by comparing the bottom equations to the top equation on that slide. Based on the result of the measurement, you cut off or throw away a part of the wave function. That is the collapse of the wave function. One sees that wave functions have two ways of changing, sometimes called the U and R process. When no measurement is being made on a system, the wave function evolves according to the Schrodinger equation, which is a continuous, predictable, unitary evolution. This is called U. When a measurement is made, however, there is the collapse of the wave function, sometimes called R, which is sudden, unpredictable except probabilistically, and non-unitary. This collapse of the wave function bothers many people, and it seems to them very weird. But as I've said, it simply reflects the sudden change in the knowledge of the observer. Probabilities of events refer to someone's state of knowledge. For example, before I knew the outcome of Jane's exam, I could only say that she had a 70% chance of passing. Whereas after I know, I must say either 0 or 100%. Since wave functions encode probabilities, they encode someone's state of knowledge. When that observer's knowledge changes, as it does suddenly at the end of a measurement, the wave function must change suddenly to reflect this. To quote Peierls again, the moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the measurement has given one result. You see, the quantum mechanical description is in terms of knowledge, and knowledge requires somebody who knows. Heisenberg himself wrote, "The discontinuous change in the probability function," by which he meant the wave function, "takes place with the act of registration of the result of the measurement, because it is the discontinuous change of our knowledge in the instant of registration that has its image in the discontinuous change of the probability function." An obvious question, and a frequently asked one, is why one needs to talk about knowledge in minds at all. Couldn't a physical device totally lacking in consciousness, say a Geiger counter, be the observer who carries out the measurement? No. Which is why Peierls, who was asked exactly this question, has answered that the collapse of the wave function required the observation of somebody who knows. The reasons were pointed out by von Neumann in the 1930s and by many authors since. Suppose the observer were just a purely physical entity, such as a Geiger counter. Then one could, in principle, write down a bigger, a more inclusive wave function that described not only the thing being measured, say a nucleus, but also that purely physical observer, say the Geiger counter. That bigger, more inclusive wave function would evolve in accordance with the Schrodinger equation. And because of that, the probability amplitudes would not collapse to give probabilities of 0 or 100%. That is a definite outcome, but rather probabilities that remain somewhere in between. That is, the bigger wave function will have an amplitude for the nucleus having decayed and the Geiger counter having recorded that, and an amplitude for the nucleus not having decayed and the Geiger counter not having recorded that. No collapse to just one of those possibilities. That is the point which we made before. As long as only purely physical entities are involved, they are described by a wave function and governed by an equation that says that the probabilities don't collapse to a definite result. One remains trapped in a limbo of probabilities rather than the world of definitely observed facts. But here someone is likely to object that observers, such as human beings, are physical. We have bodies made of atoms. The sensory organs and brains with which we carry out measurements and observations are made of atoms. Therefore, they must be describable by physics. That is obviously true. Moreover, just as one could include a Geiger counter in a larger and more inclusive wave function, one should in principle be able to include my sensory organs also in an even bigger and more inclusive wave functions. Experimental devices such as Geiger counters are just extensions of my sensory organs. Or equivalently, my sensory organs could be considered part of the experimental apparatus, just like the Geiger counter. In quantum mechanics, there's always a system that is measured and that is described by a wave function, and an observer who makes measurements and collapses the wave function. Suppose I am observing a radioactive nucleus. I could count the nucleus as the system and consider the Geiger counter, the sound waves it produces, my ears, in my auditory nerves and auditory cortex of my brain, and so on, and me in toto as the observer, as in the top part of that slide. Or I could decide to lump the Geiger counter in as part of the system, meaning that there would be a wave function describing both the nucleus and the Geiger counter, and everything else would be considered the observer. I could move more and more over from the observer side of the line to the system side. So it is somewhat arbitrary where the line between the system and the observer, sometimes called the Heisenberg cut, is drawn. Nevertheless, the logic of quantum mechanics requires that that line be drawn. And it must be drawn in such a way that there is always something on each side of the line. If one tries to put everything on the side of the system so that there's nothing left on the observer side, you end up with a wave function that never collapses and probabilities that never jump to give definite outcomes. To quote Eugene Wigner again, even though the dividing line between the observer, whose consciousness is being affected, and the observed physical object can be shifted towards the one or the other to a considerable degree, it cannot be eliminated. The way of understanding quantum mechanics that I have just outlined was once generally understood and accepted. It is variously called the traditional interpretation, the standard interpretation, the orthodox interpretation. Some use the term Copenhagen interpretation. Many objections are made to this traditional understanding. One is that one talks about the observer whose measurement collapses the wave function of the system. But there are many human beings in the world, and several of them might be observing the same system. Which one is the observer? This question is sharpened by a paradox invented by Eugene Wigner, which has come to be called Wigner's friend paradox. Wigner imagined doing an experiment employing a friend as a lab assistant. Suppose the experiment uses a Geiger counter to detect the decay of a radioactive nucleus. Late in the evening, Wigner goes home to bed, leaving his friend in charge overnight. At 3 in the morning, Wigner's friend checks the Geiger counter's record or readout and knows that the nucleus has decayed. If we regard Wigner's friend as the observer, then the wave function collapses at 3 a.m. Now at 9 a.m., Wigner shows up in the lab and finds out from his friend that the nucleus has decayed. Suppose now we regard Wigner as the observer and his friend as merely a part of the experimental apparatus being used by Wigner. In that case, the wave function collapses when Wigner knows the outcome, that is at 9 a.m. So which is it? The resolution is simple. A wave function encodes a particular observer's knowledge of a particular system. When Wigner's knowledge changes, it collapses the wave function that encodes his state of knowledge. When Wigner's friend's knowledge changes, it collapses the wave function that encodes his state of knowledge. If we want to make this less personal, one can say that a wave function encodes the knowledge of a class of observers who have the same information as each other. Another question often asked is who qualifies as an observer? A human being certainly does. But what about a chimpanzee, or a cat, or a fish, or a worm, or a bacterium, or an atom, or a subatomic particle? Where do you draw the line? One possible answer is very simple. Anything that is capable of knowing the outcomes of measurements qualifies as an observer. Another famous objection to the traditional understanding of quantum mechanics was raised by Erwin Schrodinger himself in the form of a thought experiment now called the Schrödinger's cat experiment, or the Schrödinger's cat paradox. One imagines putting a cat into a box with an apparatus that will kill the cat if a certain radioactive nucleus decays, but not otherwise. The wave function of the system, composed of cat plus killing apparatus plus radioactive nucleus, will have amplitudes for both the cat being alive and the cat being dead. Until, that is, the observer comes along and opens the box and checks to see if the cat is alive or dead. When the observer does that, he or she must get a definite result. The observer will either see a live cat or a dead cat, collapsing the wave function. Does that mean that quantum mechanics says that the cat is neither alive nor dead until someone looks? That is the impression that many people have, but it is not really what the traditional interpretation of quantum mechanics says. If I open the box, I can see whether the cat is alive or dead at that moment. But if it's dead, if I see that it's dead, I can also do all sorts of tests of forensic pathology such as measuring the cat's body temperature, lividity, etc., to determine how long the cat has been dead. Other observers may do their observations of the same cat at different times than I, but we will all agree on the time of the death of the cat if we make our measurements properly. So quantum mechanics, as traditionally understood, may be strange and counterintuitive in many ways, but it does not really say absurd things about cats being alive and dead at the same time. Many find the emphasis in quantum mechanics on the observer unpalatable. Some people think that observers are not needed to collapse wave functions because something called decoherence does it. This is a misconception. Decoherence is not the same thing as wave function collapse. Decoherence happens through a unitary evolution of the wave function, whereas the collapse is non-unitary, to use the technical jargon that I used before. To put it another way, decoherence does not pick out a single outcome as the one that really happened. No part of the wave function is thrown away or cut off as a result of decoherence. So, if one does not want to say that the minds of observers play an essential role, there are two main strategies for avoiding it. One is simply to say that wave functions never do collapse, so you don't need observers. One just has physical systems whose wave functions evolve according to the Schrodinger equation. That leads to what is called the many worlds interpretation of quantum mechanics. There's no collapse, so all probabilities remain always in play. Indeed, it is claimed in the many worlds interpretation that all possibilities are realized in some branch of a constantly splitting reality. There are branches of reality where Schrödinger's cat is alive, other equally real branches where the cat is dead. There are branches where you are watching this video. There are other branches, equally real, where you are lying on a beach somewhere, other branches where you were never born, and so on. All equally real, but in different branches of reality. Most physicists find this idea hard to swallow. But aside from its implausibility, it is far from clear that the many worlds interpretation of quantum mechanics is even a tenable idea. One severe difficulty that it has is in explaining why wave functions have anything to do with probabilities. The rule that relates wave functions to probabilities of events, the Born rule, only comes into play at the point when wave functions collapse. With just the Schrodinger equation and without wave function collapse, one does not have the Born rule, and one cannot derive the Born rule. And without the Born rule, quantum mechanics is unable to predict probabilities, and it falls apart. Because if it doesn't predict probabilities, it doesn't predict anything. Now, the other way out, the other possibility, is to change the rules of the game, to replace quantum mechanics by some fundamentally different theory. The two most popular ideas along these lines are called Bohmian mechanics and the GRW theory. I will not explain or critique these. I will only say that these alternative theories sacrifice much of the beauty and simplicity of quantum mechanics while at the same time it is very doubtful that they can reproduce all the wonderful successes of quantum mechanics. In conclusion, if the fundamental postulates of quantum mechanics are correct, and there's over 90 years of experience that suggests that they are, and if one is a physicalist, one probably has to accept the many worlds interpretation of quantum mechanics, which may not even be tenable, and which, even if tenable, is so implausible that few physicists are able to accept it. This is very heavy baggage, but the consistent physicalist must carry it. Thank you.